Okay, welcome to Astronomy 103. So we're going to talk about a property of galaxies that's both really important to understanding our Milky Way and galaxies in the universe in general, and that's called dark matter. So we're going to talk about dark matter. What is it and why do we care? And to do that, we need to talk both about the sun's motion through the galaxy and that of other stars, and then what that's going to tell us about the Milky Way's mass and mass distribution. So our sun orbits the center of our Milky Way. It takes about 225 million years to go around the galaxy once. So our sun has maybe gone around the galaxy 10 or 15 or 20 times in its lifetime. Now, because our Milky Way isn't a nice, even, single object like planets going around the sun, our sun orbits the galaxy, it bobs up and down. So sometimes it's at the top of the disk, sometimes at the bottom, sometimes it's in the midplane. And you can see its motion is kind of like the drawing of the yellow line here in this picture of a galaxy. Now, other stars in our galactic disk, they're also kind of orbiting in the same general direction of our, as our sun orbits. They might be, farther in or farther out or moving slightly differently. So we can still see them kind of move. When we look at like the globular clusters or stars we think might be halo stars, those orbits are much more likely to be tilted. They're much more likely to cut across the disk, so we'll see them moving quite fast because they're doing something very different from what we the sun, are doing. And the bulge is also a place where you might find stars in more tilted orbits. So how do we know how do we measure this? How do we measure different motions of the galaxy? And why we might want to do this is because this motion is dominated by gravity, by the effects of the gravitational force. So that's going to tell us something about mass. So when we look towards the center of the galaxy, if we pick a wavelength of light where we don't get bogged down by all those gas and dust clouds in the way, we can actually physically watch stars orbit over decades you can see a picture here. The background picture is a monochrome picture. It's been color tinted so you can better see the stars. And you can see it's pretty blurry. This is a picture that's been zoomed in a very great deal. And you can also see what's drawn on top of it is the measurement of the star's orbits over decades of observation. And from this, we learned that in the center of our galaxy, an object we call Sagittarius A star, SAG-A star, is a rather large, what we call a supermassive black hole. It's it's millions of times the mass of a normal black hole that might form when a star dies. So it's really interesting, but we're not going to talk that much about it. So because you've got a lot of mass in a small space, you can easily see the motion of stars. As we go farther out, we're going from stars that might take decades to orbit to stars that take millions of years like our sun. We're only getting a small picture of that. So we can measure, for instance, all the stars, how they're moving relative to the sun, and we can measure our sun's motion relative to farther away objects. If those stars are nearby, we can get their motion relative to the sun pretty easily by just sitting and watching for decades and making very careful measurements. That helps us kind of map out our local neighborhood. But a lot of stuff is just too far away. We can't physically see this move across the sky, even if we take really precise measurements over decades and decades. So what we do is we can't see things move in the right ascension direction or the declination direction, but we can still see things come towards and away from us using the Doppler effect. That's not distance dependent. That's just telling us how fast is this thing moving towards us or away from us, not, how much distance it's covered in a year. So we can use this to make kind of a 1D map of all over our galaxy and pick up the patterns and get a more detailed look at like our neighborhood. So we do this. And why are we doing this? We're doing this to get the mass distribution of the galaxy. We want to know not just how massive the Milky Way is, but where is the Milky Way keeping its mass? So gravity is going to set whatever the orbital speed of an object is. And two things are going to play into that. One is the distance from the center. and the other is how much mass is inside the orbit of that star, planet, whatever. So let's start with a simple case, the sun and the solar system. We've talked about this one before, way back in the beginning of class when we were starting to talk about orbits and gravity. So if we measure the orbital speed of Neptune, let's say, and we know how far away Neptune is from the sun, we can then get the mass of the sun plus Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus. And then if we do the same for Mercury, we have just the mass of the sun, so we can figure out the mass of the planets. And from what we learn is that it's really hard to get the mass of the planets by this method because they're all much, much less massive than the sun. Neptune's motion is dominated by the mass of the sun. We can still kind of tease out the gravity of the other planets, particularly Jupiter, Saturn, and Uranus, but it's really hard. So for a system where most of the mass is in one central object, you get something like the graph on the right for when you plot orbital speed versus distance. This is just going to be Kepler's third law. And what this is telling us is that basically all the mass of the system is in the sun with little crumbs left for the planets. So let's look at the Milky Ways. So it's at the bottom. The observed Milky Way rotation curve is the red one. So first you can see our numbers are much bigger. They're bigger by a factor of 10 at least. And our distances are bigger. Instead of AU, we're looking at kiloparsecs, 1,000 parsecs. So, all right. For the Milky Way, most of the mass is spread out in stars. There is that supermassive black hole in the center, but it's not a major component of the Milky Way's mass. It's pretty big, but the galaxy is bigger. That means instead of the stuff moving, that means instead of the fastest moving stuff being close to the edge, the stuff in the bulge takes a bit, starts out moving relatively slowly, and again, relatively, and picks up speed as you go maybe the first few kiloparsecs from the center of the galaxy. And instead of the speed going down with distance, because while we're going farther away, we keep adding more mass, it stays roughly level. Our sun's at about 8-ish kiloparsecs. So you can see the velocity at 3 or 4 or 5 out to maybe 12, 13 kiloparsecs is all about the same. So the galaxy doesn't rotate like a CD in that the outer bits are moving faster than the inner bits. And it doesn't rotate like our solar system where the inner bits are moving faster than the outer bits in terms of velocity. It rotates such that most of the galaxy all moves at the same speed. The farther away stuff still takes longer to orbit because it just has more distance to go. So you can imagine a bit like cars or runners on a track. They're all moving roughly about the same speed, but the ones on the outside have to move a larger distance around the track. Hence you see those staggered start things. Now, the thing is, though, is when we look at the galaxy, we notice after about maybe 15 kiloparsecs, our galaxy is about 30,000 parsecs wide, so about after 15 kiloparsecs, we don't see any more stars and gas and dust. So it should start going down after that. It's fine if it's level where we see the stars and gas and dust because we're adding more mass, but we're not seeing any stars and gas and dust, which has mass, out past 15 kiloparsecs or so. So what we should be seeing is a blue curve. But again, when we keep looking at measuring cool gas clouds and globular clusters, we see the red curve. So what's the deal? So, well, the answer that's accepted by nearly all astronomers is, well, clearly there must be mass. It's not stars. We see stars. It's not gas clouds, because either we'd see the gas clouds giving off light. Even cool gas can give off radio waves. Or we see the gas clouds absorbing starlight. Maybe a small bit could be smaller objects, like brown dwarfs. But we really aren't seeing it. So we're going to give it the name of dark matter. It's matter because it's has mass. It's affecting gravity. That's how we see it, or see it in quotes. And we're calling it dark matter because it's not interacting with light. Now, to clarify, that means not only is it not emitting light, but it's also not absorbing light. So it's more transparent matter than dark matter, but the name sticks. Now, we know roughly about the size of our Milky Way's halo from the globular clusters. Remember, they're all kind of, they and a few stars are all kind of orbiting our galaxy. They're nice little test particle probes to tell us the mass, help us make this rotation curve. And as far as we can tell, the dark matter halo, the collection of dark matter around our galaxy, is roughly spherical and extends past the globular clusters. Our galaxy is sitting in a massive amount of dark matter that's maybe 5 or 6 times the mass in stars and gas and dust. In fact, this may be our ultimate definition of a galaxy, is it's a collection of stars and gas and dust that sits in a dark matter halo. So, all right, when we look at other galaxies, we see the same kind of thing. It would be really unusual to see a galaxy with little to no dark matter. Again, it seems to be a defining trait of galaxies. We also see this in galaxy clusters. So when galaxies tend to cluster, they tend to be near other galaxies. Makes sense. Gravity is a big important force. It means matter tends to clump up and be near more matter. But when we look at galaxy clusters and we measure how fast the galaxies are going, and we estimate their mass from looking at stars and gas and dust, the galaxies are going too fast. They should escape from the cluster, but they don't. So that tells us, again, there's more unseen matter. There's more dark matter. And we can also measure the gas using a principle from Einstein's general relativity we call gravitational lensing. Basically, mass slightly distorts space-time, and light likes to move in straight lines, moves in beams of light. If you mess up space-time, the light looks like it's bending, even as it is trying to take the straightest path. So we see these distorted images when we look at a galaxy cluster and look at the background galaxies, look at the galaxy behind it, and they're kind of distorted and weird. So I'm going to point out this image that I'm showing. It's called the bullet. This particular object is called the bullet cluster. This is an important discovery when it comes to dark matter. It was done in the last 10 or 15 years. So, all right, let me walk you through this. So the bullet cluster is actually 2 clusters of galaxies looking way off in the distance. These 2 clusters collided, and they've kind of passed through each other. The individual galaxies are pretty small compared to the cluster, so none of them collided. They just went straight through each other. But galaxy clusters tend to attract a big cloud of gas is sitting around the galaxies, which is visible here in red. And when those 2 big clouds of gas ran into each other, they heated up, they started interacting, and they kind of got left behind. So here you have a visible light picture showing you where all the galaxies are and pointing out the 2 clusters. You have a red picture, which is the hot gas in X-rays, showing you where the gas is. And here's the important thing. When we count all the stars and brightness in the galaxies, we get that their masses should be some number. When we measure the hot gas and estimate how much mass is in that it's most of the cluster's visible mass is in that hot gas that was kind of left behind by the clusters when they collided. But what we can do is take that gravitational lensing, look past the clusters, look at the whole region, look at background galaxies, measure how distorted they are, and use that to make a map of where the total mass of this cluster is. So we do that, or rather astronomers do that. And the blue is roughly where they think, is basically a mass map. There's more matter, there's more stuff in the blue regions, and there's less in the regions that aren't tinted blue. We know this because of this gravitational lensing. So the red is telling us where say nearly 90% of, 80 or 90% of the visible mass is in the red. But that doesn't match up with where the total mass is. There's a bunch of invisible mass that's meaning that moving with the galaxies rather than with the gas. And so if that matter acts like the, the individual galaxies, it can just pass through, two clouds of it can just pass through itself without colliding or anything, then it will follow the galaxies. And it seems to. So this is telling us that here is the dark matter and here is how it behaves. It is not moving with most of the visible mass of this cluster. So, all right, what is this stuff? Now, some of it might be things that are just really hard to see. Old brown dwarfs, they're very cold, they're very small, they're hard to detect. They're still emitting and absorbing light and other kinds of electromagnetic radiation, but they're just a good way to have mass that's mostly dark. But based on, some of the other principles we've looked at, based on some of the studies we've been doing of the early universe, we start to think that most dark matter is not normal matter at all. It's not just normal matter we figured out ways to hide. Now, our name for this is non-baryonic matter. Now, what is baryonic matter? Baryonic matter is like things like protons and neutrons and the stuff that makes up all the stuff you're interacting with on Earth. Non-baryonic matter would be something that's not protons or neutrons, or the associated particles. So we don't know what this is. We know what it isn't, but we don't know what it is. We know and we also know it seems to be about 5 to 6 times as common as normal matter, which means that most of the matter in the universe is dark matter, and we really don't understand it. So what the astronomers have to do is we make all the observations we can of this stuff's gravity and how it interacts or how it doesn't interact with things. And we then call up our friends, the high energy physicists, and we say, hey, we found these, we need a really weird particle. It's not going to do anything weird like radioactively decay or something, that has these properties and can make up 5 to 6 times the ordinary matter in the universe. And then they go to their big old particle accelerators. This is a map of the CERN particle accelerator. It is on the border of France and Switzerland, and it is huge. You can see the towns labeled on this map. There's a smaller particle accelerator out near Chicago called Fermilab, and among other things, they keep a herd of bison inside the ring. So these are really big scientific facilities. They slam normal matter into itself at large fractions of the speed of light. They make really concentrated explosions and look for weird particles, things like the Higgs boson, which is discovered. That's not dark matter, but it's something else they found here. So they're looking for candidate particles, things that trying to make dark matter or make something and identify the thing they made as dark matter. So do we need it? If I tell you there's this invisible kind of matter that doesn't really interact with anything except gravity, and we haven't found it yet, and our particle physicist friends are stumped, do we need it? And the answer seems to be that most astronomers think or it's the best fit to most astronomers think it's the best fit to our observations, this hypothesis. But a few, just to be rigorous, are saying, well, what if we just don't understand gravity at large scales? What if our just understanding of how gravity works is just a little bit off? We don't really notice it in the solar system, but if we look at big things like galaxies and clusters of galaxies, we get the wrong answer. And to some extent, that's why they were testing the thing with the bullet cluster, because if we didn't understand gravity, we'd expect that most of the mass would have been staying with the mass we see. We would have seen the effects of mass matching the effects of the visible mass. And the other problem with maybe we don't understand gravity is that we've done some pretty good detailed tests in the solar system. We've measured the effects of Einstein's theory of general relativity at a very large scale as we, for instance, talk to spacecraft that are orbiting the outer planets. We can measure, if we talk to them while the sun is in the way, that lets us measure how the sun is bending space-time, making us a really good test for Einstein's theories of gravity, that mass bends mass alters space and time. And we've done those things like find black holes using gravitational waves. So currently dark matter is our best guess, and it's just really frustrating that we don't know what it is besides knowing what it isn't. So in summary, stars orbit the center of our galaxy. Unlike our solar system, the rotation curve of a galaxy is pretty flat once you get out of the bulge. Based on this, we have to conclude that our Milky Way and other galaxies sit in this halo of dark matter, which is not normal matter. It's not protons and neutrons, and we don't know what it is. So next time, well, while we're talking about galactic motion, let's talk about spiral galaxies. You know, the most characteristic feature of our Milky Way and galaxies in general are those spiral arms. What's the deal?